So now we are going to pick back up with chapter 15, section 2, Lewis acids and bases. So here we're going to explain the Lewis model of acid-base chemistry, write equation for the formations of adducts and complex ions, and perform equilibrium calculations involving formation constants. So chapter 14 was all about Bronsted-Lowry acids and bases, but in reality, there's a lot more types of acids and bases. It's only applicable to reactions that involve proton transfer, but there's more to it than that. So G.N. Lewis came up with a less restricting model, where a Lewis acid is defined as something that accepts a pair of electrons. So it takes them, whereas a Lewis base donates a pair of electrons. And the Lewis acid-base reaction makes a product that has a coordinate covalent bond. So now we have to change our thinking. In chapter 14, we were looking at where protons go. Now we need to think about the electrons and where they're going and what they're doing in the reaction. So a coordinate covalent bond, or dative bond, is a type of bond that forms when one of the atoms in the bonds provides both bonding electrons. So for instance, we have water here reacting with H+, and the oxygen here is providing both bonding electrons when it bonds with this hydrogen. In the ammonia, same type of thing. The nitrogen here has the two bonding electrons that it's providing to grab this hydrogen. A lot of species that behave as Bronsted-Lowry bases will behave as a Lewis base, because in order to accept a proton, it has to have an atom that possesses a lone pair of electrons. So some anions and neutral molecules that have lone pairs, like amines and water, can serve as Lewis bases. Protons can serve as both Bronsted-Lowry acids and Lewis acids, but most Lewis acids are not Bronsted-Lowry acids. Cations and electron-deficient molecules tend to serve as Lewis acids. And this model, the Lewis model, really expands the number of species that are considered to be acids. It broadens our horizons, if you will. We form an adduct. So a Lewis acid-base adduct is a compound that contains a coordinate covalent bond that is formed between a Lewis acid and a Lewis base. So the adduct is your product. So there's some different types of adducts. So if you have two Lewis bases reacting with one Lewis acid, you form this guy like you see here. We have the silver in the center, and you have the two ammonias on each side. Going back to generic, you have a one Lewis base with the Lewis acid forming that generic adduct. If you have a Lewis base like here, O2 minus, and your Lewis acid, this SO3, the adduct, acid-base adduct you formed there on the right. So you see all these different types of adducts that can form based off of these reactions. You can have an acid-base adduct reacting with another base to form a new adduct and a new base. Okay, so there's a couple examples there. There's all kinds of them. So as you probably can tell, these adducts, a lot of them are complex ions. These are polyatomic ions that have a central atom. A lot of times it's a transition metal that is surrounded by ions or molecules called ligands. And these ligands are Lewis bases. So for instance, we have the silver here, our central atom, and it's got these two Lewis base ligands. In this case, there's two ammonias on either side of it. The charge of the complex ion is equal to the sum or the charges of the ligands, the sum of the charges of the ligands and the central atom. The formation of it cannot be predicted. It has to be determined by experiment. So you can't go, oh, this is going to be what forms. You have to actually experiment. And that central atom-ligand bond are coordinate covalent bonds. And sometimes these complex ions can be called coordination complexes. Coordination chemistry is really interesting. Here's another example, copper with a cyanide ion, making this copper cyanide complex ion. And then we have what is called the formation constant. So yet another constant. And this is the equilibrium constant of formation ion components. It can be very large. The Kf for this reaction, come on, pen, wake up. So again, the Kf for this reaction is equal to our product, which is our concentration of that, which is the complex ion, divided by our Cu plus times our Cn minus squared. Okay, got that 2 in front of it, so you got to make sure you square it. The inverse of the formation constant is the dissociation constant. So formation versus dissociation. And it is literally 1 over Kf. So it is the equilibrium constant for the decomposition of a complex ion into its components. Okay, so in this case, Kd is Cu plus times Cn minus squared over Cu Cn2 minus. So it's 1 over Kf. It's the inverse. So let's go ahead and look at an example. We want to calculate the concentration of the silver ion in a solution that initially is 0.10 molar with respect to this silver ammonium complex. So we're going to go ahead and use our good old ice table. So to make this, we have to have Ag plus and 2 NH3 minuses. Then this is going to form Ag, and sorry, this should be a 2 here, like that. NH3 2 plus. Now, everything here is aqueous, so we cannot say, oh, I'm not using NH3. Everything is aqueous. There's no water to cancel. And we're told that initially we have 0 ammonia, 0 silver, but we started with 0.10 molar of the complex. So we're looking more at the reverse reaction. So we're losing some X of the complex, gaining some ammonia, gaining some silver. So at equilibrium of X, X, and 0.10 minus X. So our Kf, our expression then is products, which is the AgNH32, so that's 0.10 minus X divided by our X times X, so our reactants. So the Kf also, when we look it up, is 1.7 times 10 to the 7th power. So we can use that and say, yeah, this is way more than X. So we can get rid of that X in the top. So now this is equal to 0.10 over X squared. I'm sorry, X, this should be 2X, and this should be 2X, and that's squared. Sorry about that. So then that is 0.10 over 4x cubed. So then going ahead and solving for x, we get that it is equal to 1.1 times 10 to the negative 3rd power. If you need me to go over how that I got that, just send me an email or a text. But I figure you guys should be good with your algebra for solving for x there. But again, it's no problem. If you need me to go over it, just let me know. And this is a really small amount, so this also justifies using that assumption of x being much less than 0.1. Actually, I should probably rewrite this as x is much, much less than 0.10. That Kf tells us that it is. So now we have our amount of x, and we want to figure out the concentration of silver, so that's our concentration of silver. If we wanted the concentration of ammonia, we multiply it times 2, and if we wanted the amount of our complex, then we would take that away from 0.10.